Right, so today I thought what we'd do is we would use a different programming language called Julia and the machine learning toolkit that's native to that language called Flux to repeat the stuff we've done in TensorFlow and PyTorch with the FashionMNIST dataset. So, first question you might be asking is why do we want to do this in a different language, right? And it is a bit frustrating that we have lots of perfectly good programming languages, and rather than improving those, people go off and invent other ones. But I think in this instance, the developers of Julia are trying to service a need that really is there, right? So the dominant languages in HPC are Fortran, C++, and Python. All of these are imperfect. Fortran, by far and away the oldest, it's got 66 years of history, is very good at doing maths, it's very performant, it's very good at writing code that's close to the metal. You can program GPUs in it, you can program CPUs in it. But it has some features from its age. For example, 66 years ago when it was invented, there was no such thing as a hierarchical file system. And throughout that long life cycle of the language being improved and standards changing, that hasn't been resolved. There is still no real good way to deal with directories and things like that. One of my favorite Twitter accounts, there's a Twitter account which tweets out like Fortran tips, and their tip for how to list the contents of a directory was to fork ls and read the output, right? This is not a thing. So Fortran, and Fortran also is quite annoying sometimes to read and write files, never mind looking at directory structure and things like that. Python is extremely popular, but almost everyone uses the reference implementation, which is called CPython. Most of the libraries are only compatible with that reference implementation, and it is incredibly slow. It's one of the slowest programming languages. That's meant to have been improved in Python 3.11. I've not really played with that yet. I've just got a new laptop and it has Python 3.11, so I'll have a play at some point in the near future. But it is generally painful. And the way we achieve performance on Python, right, is when you're running something like TensorFlow or PyTorch, they are calling out to libraries written in other languages, usually C or Fortran or CUDA or whatever. And that brings with it a packaging nightmare. So when you install a Python library, you have to install a bunch of dependencies that are from another programming language that compiled another programming language. All that dependencies for that become a problem. It's a real pain to get your workflow up and running. C++ is very flexible, but it suffers from it. And also it looks hideous. The syntax is horrible. C++ allegedly has standards. I say allegedly because, you know, it's not. And it's just generally unpleasant. So why Julia? Right, so Julia is an attempt to create a future language for scientific computing. And the development is about a decade old. And the initiators of the project really set out with a set of demands they described as being greedy, right? They wanted a language that was expressive and extensible like Python, was performant like Fortran, so they used LLVM to make sure it does just-in-time compilation of your code. So you write code, you don't ahead of time compile it. When you run your code through the interpreter, it actually JITs it and turns it into native code. There are some benchmarks, but this has been even better than like good Fortran compilers like the Intel compiler. They wanted really good accelerator support, both for AMD and NVIDIA. Things being what they are, NVIDIA, of course, has the best support. AMD is lagging behind a bit. And I think there is even support for the metal stuff in the Mac, but it's very embryonic. It has built-in package management and virtual environments. And for our purpose, we're going to use the ML toolkit Flux, which exists, right? So why would you not want to use Julia? So with its youth, Julia has gone through quite a lot of changes, quite a lot of growing pains. Up until about version 1, the syntax was changing almost continually, and the net effect that had was that if you went and found a tutorial or a course on how to learn Julia, it was basically worthless. It was effectively describing a different programming language from what you would get if you downloaded the current set. That is largely resolved post version 1, but this kind of problem is still reflected in the actual software, in the library packages. Flux being a terrible example, where fundamentally most of the examples you find don't work because the library's gone through a massive restructure. The documentation is already also fairly technical and over-engineered. It's quite clear that the Julia people are keen to do the software right, But this means that the documentation is quite hard to read if you don't understand the underlying data structures they're using, or there's a lot of implied knowledge in the documentation. And when it comes to the examples, and this is definitely true with Flux, their examples tend to be like a good software engineering example, not how do I do X, right? And those are very different things. The built-in package manager is not perfect. Certainly once you start getting complex workflows, I found sometimes it just decides to not download packages and then we'll download them and run it again. It tries to be too clever at times. So a good example is if you install the CUDA library on a node which doesn't have a GPU and then try to run on a node with a GPU, you get a nice error saying, well, you should have done this on the node that had a GPU. And that's quite annoying. And the final thing is, we're early in the lifetime of this language, so there's not a lot of... There's usually one project that does the thing you want, but it might not be well maintained. It's one guy, whatever. So let's look at Julia, right? We have Julia on our HPC systems. Let me bring up a terminal. It's installed as modules. We have Julia 1.85 installed, which is the most up-to-date at the moment. That should not be taking that long. There we go. If we import that into our environment in the usual way, and run Julia, it should start up Julia 1.85. One of the problems with having stuff on network share is the first time, it's going to be cached and whatever. So let's have a play with the language. So if we go into our Scratch base and create a directory. Right, we can do something like, we start Julia. Once it's started, it's a programming language. It's got very good support for UTF and Unicode, which means that it's quite expressive. You can use lots of your fancy mathematical symbols and have them reflected. So for example, your epsilon, rather than calling it epsilon, or it helps if I can type, E can actually be an epsilon in the code. You can do kind of the usual things with that, it's the usual maths. Oops, hit the tab again. Yep. You can, sometimes you get tricked. So you can do in the normal way 5.02 and they get 2.5, but there is a integer division symbol which looks like that, and it will do integer division, i.e. rounding down. The packaging stuff is accessed by pressing the right square bracket, and that takes it to the package prompt. And from there you can, for example, turn this into, activate dot is the equivalent of creating a virtual env in Python. And then we can add a package to it. So let's call add in bson, which is an encoding library. I've very deliberately cleared out my .julia folder before this, which is where all your settings and stuff is stored, because I wanted to show this from a vanilla setup. That's installed, it's ready to go. You get out of the package by either pressing Control-C or backspace. And then you can say using bson, and it's in your environment. Okay. If we get out of Julia and take a look at what that's actually done, so it's got these two toml files. One of these, the project.toml, lists the packages that we actually asked it to install, and then the manifest. What I'm going to do now in preparation for our next thing is, right, let's talk about Flux first. So, Flux. So Flux is a machine learning toolkit for Julia. It's somewhat lower level than PyTorch, and you have to write a bit more of the plumbing. I couldn't find a good FashionMNIST example, and this is kind of where I started going down the rabbit's hole. They've got, where are we? Obviously, there's the Flux website. They've got this thing called the Model Zoo, and here I kind of describe what I mean about things being really over-engineered, right? it's quite clear that this is like a proper program for training. It's broken everything down to functions. There's a lot of stuff that's not well explained. It doesn't really explain what one-hot batch does. It uses these mysterious data loader functions, which actually I'm not going to show in this tutorial. And it's not very good. I did spend a lot of time looking around for various examples of how to do this, usually with MNIST rather than FashionMNIST, because I don't know why they don't. It's not common. And I found a lot of different implementations using radically different code, some of which worked in present Julia and Flux, some of which didn't. There's some particular gotchas around the dimensions that arrays have that I'll talk about in a bit. It wasn't a great experience. So what we're going to do is we're going to take what other people have done to show an MNIST example, and we're going to take the neural network, which is in this, particular version here, which is a thing called Linnet 5 and this is where I'm definitely repeating things I've read and not understand, with a ReLU activation function rather than a sigmoid one. Whatever, it's machine learning stuff. But at a high level, let's look at what we're going to do, right? So the data set is a set of images. They are grayscale 28 by 28 images of clothing. These are associated with labels which say have a number which says which of 10 categories that image belongs to. What we're going to do is going to split that into two sets of data, a training set and a test set, because your test set should always be different from your training set. We're going to take that LNet 5, whatever, model, and train it with the training set. So produce a train model. And then we're going to take the images from the test set and run them through that model, and hopefully it'll get the same answer as is in the labels, right? So I've coded this up, and the code is here on GitHub. So let's bring that up. Right, in this repo, we have some dependencies. So I wrote one of those little libraries that shows stuff in the terminal again, this time using 256 color terminal features of the terminal, called TermShow. And I've written a bunch of stuff in the fashion folder here, right? There's a project.toml. You generally don't ship the manifest.toml. You get you kind of reconstruct that on the target machine. And that's got a bunch of libraries. So it's got bson, which we're going to use to encode the model at the end. It's got CUDA, because we need CUDA, because we're going to be doing stuff on GPUs later. It's got Flux. Flux is the machine learning library we talked about. It's got these two libraries. MLUtils provides some tools for reorganizing the arrays, and ML datasets is where we're getting FashionMNIST from. And finally, there's a little tool which shows progress meters. There's a bunch of Julia programs in here. There is what I've called simple. This really doesn't work. It's got a very bad model, which is just 2 dense layers. This was really when I was starting up trying to get the process going. I had real difficulty getting the Linnet model to work because when it uses, and if I switch over to that, some of these layers need your array to be in more dimensions than it's in, so particularly the convolutions. So if you think about our data set, it is images that are 28 by 28, and this really wants 28 by 28 by 1. That's obviously the same data, it just has an additional dimension added, and this is what this unsqueeze function from MLUtils does. Sorry. I've also done a GPU version of the code. There's a script which sets up all the libraries, and we'll run that in a minute. I've got a tiny program here which you can run on a trained model to actually get it to pick images out and show them. This was just me playing yesterday. So let's actually bring that up on the cluster. So I have, back in this terminal, I believe, I'm logged into a compute node here. Excellent. Let's do git clone. Let's get this code. Okay. Right, that is now in there. So we go to Julia ML. Go to fashion. The setup script basically starts up the environment, enables the package manager, and uses it to instantiate what's in the project internal. So let's run that. Need to add it to my environment. Okay. So obviously, Flux has a lot of dependencies, right? And one of the things you'll find, one of the negative experiences I found using Julia is you do spend a lot of time watching packages download and precompile. That's just part of the experience. The advantage is when you're doing the precompile, after you've done the precompile, code runs very quickly. And so it's, it is worth it, particularly if you do stuff for production. When we're doing test examples like this, it's kind of annoying because it takes a while to do things. So we're going to leave that in the background while I carry on talking. Right, so let's look at the code. So obviously at the start of the improved.jl, there's some stuff where we bring in dependencies. But then the actual steps we go through, going back to that flowchart, is the first thing we have to do is you have to bring in the data sets. So the ML datasets package has that. You can pull there's a predefined split of training and test data that you can use by passing this argument. You can then split it into X and Y, with X being the images and Y being the labels. And then you can pull the categories out of the metadata for the data, and that has the mapping for class names to the integer, which represents the class in the set of labels. We then use onSqueeze to jiggle the dimensions about and increase the number of dimensions. And then on the labels, what we want to do is we want to convert them from being an array of numbers to a two-dimensional array of probabilities that they are a particular number. And we use that with the one-hot batch routine that's in Flux. The model is literally just straight out of the example in the model zoo. I've just pulled out some of the stuff where it tries to be clever and pull dimensions out of things. We don't need that. We know what size things are. We just want to make this as simple an example as possible, right? Then to train this, we need to define some things. We need to define a loss function. There's a pre-built-in loss function we're going to use from Flux. The optimizer everyone uses is add-on, which is an improvement of some generic optimizer. I'm going to set a number of epochs. In this case, I'm going to set 40 because we're going to run on CPU first, but we can run easily on 400 on GPU, and we'll show you that when we're on GPU. We then merge the training data, the labels, and the images into a new array, and then we loop over the epochs running Flux train on them with that optimizer and the training data. Then when it gets to inference, we pull in the test data in the same way, with the difference being that we don't need to convert the labels Y into a probability matrix, because we don't need that. We just want a mapping so that when we get a probability matrix out of the model, we can then convert it back. We're going to do two things. We're going to estimate the accuracy, which is how many of the guesses are correct, right? So we're going to loop over all the items in the test sets. We're going to pull out the image, increase the dimensions again, because we need to do that, because we're going from having effectively a single image to a list of single images. We then run the model on the fixed image, use findmax to find the highest probability out, compare that to the value that's in test Y. There's an off by one error, which is fun. And if they're correct, we increment the sum and eventually work out the accuracy as being the sum over the length of the set. And then we'll do our traditional ankle boot. We'll pull out the first image, do the same thing where we bump the number of dimensions up. We'll render it to the terminal, and then we'll print out the guess, and hopefully we'll get ankle boots as the answer. So let's do this, right? Hopefully we've done the install now. So here we see what I mean. See, info packages marked with an arrow are not downloaded using the instantiate to download. So let's run setup again. Oops. I don't know why it does this. It does it with the CUD in every time. So it's not like it's a dodgy server. It's just something it's decided it's not going to download this on the first run through. And meanwhile, over on another terminal, just to prove we're on, because we'll do it on a login node so that we're definitely doing it on CPU. CD, what's it called? Julia ML? Let's see if that's done. Okay, fantastic, so that's done. Right, so let's switch over to the terminal where we've got CPU mode. So let's load Julia, and then we need to activate our project. And then we should just be able to include improved.jl. Now, because this is the first time we've run this, and it hasn't downloaded the data, the first thing it's going to do when it gets to the ML datasets part is ask us for permission to download the data. This is nice. I like it when things ask me permission to do things and don't just go ahead and break. There we go. Yes. This can sometimes time out, which is a bit annoying. Let's see if it works. There we go, and now we'll do our training. So the first thing it's doing now is loading the data. I haven't played with data loaders here. I suspect the way they work is they create an iterator so you can start working on the data before you've loaded it. It's particularly notable, and I might show it with the GPU stuff, that when it's loading you can watch the memory usage on the GPU go up massively while it's doing it. And here we go, so now it's training, right? So this is that progress meter dependency I included. If we quickly look at the code, you will see that it's got this sort of decorator you put around a for loop, and that just causes it to show that progress meter and calculate the time and all sorts of nice things. So it currently thinks it's going to take 16 minutes to do. It's only doing 40 epochs. That's quite slow, quite annoying. So let's go back to talking to the next step in the talk and talk about doing stuff on GPU, which is quite easy. And if we time this right, we will overtake the work it's doing here on the CPU by doing the GPU. So let's bring up the talk. Moving to GPU. So Flux makes it very easy to move to GPU. Flux contains a function called GPU, and you just need to make sure you put it on. You put your model and data on there. Flux, Julia, in fact, has this nice pipe, like a Unix pipe, for sending things to functions. And we use it here to put it on the GPU. And then, just to show off, we're going to use the CPU for inference, because one of the problems with PyTorch is that models you train on the GPU are not easy to run on CPU and so on. We're going to show we can do that in Julia. And you can do that in the same way. There's a CPU function, and you just pipe your stuff through that. So if we look at the code, if we look at the GPU version of the code, you'll see that we've brought in CUDA as one of our dependencies. And here we are using this pipe construct to put the model on the GPU, as well as all the training data. I think that's not actually necessary, because later on, after we merge the data together, I've put the whole thing onto the GPU. In fact, let's just prove to ourselves that's not necessary by taking that out. Let's see if it works. And then you just do the training as normal. we need to bring it back here, so this is bringing it onto the CPU. And that should be all fine. Right, let's get that out. So if we go over to here, I'm logged in, back where I did the build, I'm logged into this compute node E96A. It has a V100. We load Julia as before, and activate the project. There's actually a syntax you can do for doing this without going into the package mode. Where you do using package.activate. I just like this, makes me happier. And in this case, we're going to include the GPU version. Now remember, this one is written to use 400 epochs, so it should be, it will be A, faster, and B, a much better, it's training more, so it should get you a better model. We won't need to download this because we already did it when we did it on the CPU code. How's the CPU doing? Well, the CPU has still got 7 minutes to go. At this point, it's now transferring the data over to the GPU. That takes a while. It takes a while to load it anyway. It takes a while to transfer it. If I switch over to another terminal where I'm logged into the same node, I should be able to see. Ooh, not yet. There we go, processes. So this is my process here. And gradually it's going to grow until it's loaded all the data into the GPU, right? There we go. Oh look, 400 epochs is going to take us, ooh, watch as it falls. So the CPU is still going. And the GPU is presumably now completely overtaken it. And we'll finish shortly. There we go. We've got an accuracy of 0.87. We got our beautiful grayscale ankle boot. And it's gotten it correct. It's decided it's an ankle boot. The CPU is still chugging away. Okay, so what have we learned? How to load Julia into our environment in the UCL HPC systems. You just do modulo Julia. I tend to keep the Julia package up to date. If the latest one is not there, you can ping me personally and I'll update it. We've shown how to create a Julia project and install some software packages into it. We've shown how to use Flux to train a model on the MNIST fashion set and how to run that on GPU. And of course, we've got our lovely ankle boot. There are some final things. There are some surprising frustrations you might have in Julia. One of the things that caught me out is some of the scope is a bit complicated. So let's bring up a new terminal. If we create a file with a loop in it, sorry, Alright, so we create a loop. It'll give us an error about scope, which is fine. Scope is fine, it's fine for the scope to be more complicated than that. But here's a problem. If we just paste that into the terminal, which is what include is meant to be the equivalent of, works fine. That's quite annoying. There's some other things a bit like that. When I was doing some of the development, it wouldn't let me do certain things on the GPU if I was doing it in a program, but it would let me do it interactively because it decided it wasn't efficient when I was doing a program. There's lots of things like that which might catch you out. But, you know, it's nice language, usually. Let's see if the CPU's finished. The CPU is still going. Maybe we'll hang around for 1 minute and 15 to see if we can get the output. Sorry, I'm not sponsored by Leon. They're convenient. Just to be clear, Pret, also good. There we go. And, you know, so the accuracy here was 0.72 rather than 0.87-ish. But I did get the ankle boot. Sometimes it doesn't. Okay, so I hope this talk was interesting. Julia has a very active community, both on Twitter and they've got something called Discourse. If you need help, definitely reach out and ask people. They're very friendly and very helpful. This is probably the thing that can save us from all having to learn C++ to do accelerator programming. So, you know, good luck and have a nice weekend.